Okay, um, in this video, okay, we will continue with everything we have learned so far, especially an application of Gauss's method. We have already done plenty of examples about Gauss's method, but especially how to describe a solution set in using vectors notation. So this is what today's tutorial is going to be about, because so far we all know how to perform Gauss's method, how to get the echelon form of a system. We also know how to detect the three different solution set types, and we also know how to describe a solution set, especially when it is infinitely many solutions. But so far we haven't had an elegant way of describing that solution set. Okay, that's why we made a small pause and reviewed matrices and vectors. Okay, so the vectors notation will help us to describe the solution set we have already seen in a more elegant, okay, and intuitive way. Okay, so let's do today's tutorial example. Okay, so let me split the board. Let me change color and write down the question. The question says, solve the, what is happening? Okay. Okay, just 1 second. Okay. Okay, now let's go. It says solve the following system of equations using matrix notation. Okay, but that means we need to write the system as an augmented matrix. Okay, as we have already seen, it makes the computation easier. Okay, and then they say to express the solution using vectors. Using vectors. Okay, so what is the given solution system? Is minus x minus y plus z plus 2w equals to 2. Okay, that's the first line. Then we have minus 3x minus 2y plus z minus u equals minus 3. And 4x plus 3y minus w plus 2u equals 2, 5. Okay, so now let's find the solution, or let's answer the given question. Okay, so step number 1. Let me change color. I like colors. So we need to write the augmented matrix, the system, as an augmented matrix. Okay, so step number 1. Okay, let me write step 1. So step 1, augmented matrix. Augmented matrix before we perform Gauss's method, okay? So here is the associated augmented matrix. If you remember, we said that the augmented matrix has two parts. On the left-hand side, we have the coefficients of the variables in the system. So here we have -1, -1. So the coefficient of x for the same equation, for the first equation, sorry, is -1. The coefficient of y for the coefficient of y is -1 as well. And for z, the coefficient is 1. It's just 1. It's just 1. And for w is 2. And we have another variable here, which is u, but its coefficient is 0. That's why we have nothing there. So that's 0. Okay. Let's continue. As for the second line, the second equation, so we have -3, -2, 1, 0, -1. And for the third equation, we have 4, 3, 0, -1, and 2. Okay, and then so that's the first part of an augmented matrix. The second part is to the right hand side of this bar, we have the constants here. So we have 2, -3, and 5. So that's the associated augmented matrix. Okay. The second step is to perform Gauss's method. Okay, and to bring the system to its echelon form. So to bring this matrix to its echelon form. Okay. So here, step 2. Gauss's method. So basically, when we are asked to solve a system of linear equations, these are the steps we need to go through. Gauss's method. Gauss's method to get the echelon form. Okay, to get the echelon form. So let's perform Gauss's method with the augmented matrix. Yeah, here is going to be our original matrix: -1, -1, 1, 2, 0, -3, -2, 1, 0, -1, and 4, 3, 0, -1, 2, 2, -3, 5. Okay, so now let's perform Gauss's method. The first step is to use the leading term, the leading entry, okay, in the first row to eliminate the entries in the rows below it. Okay, we all know how to perform Gauss's method, so let me go through it quickly. So to eliminate the -3 here, we need a -3 times row 1 plus row 2. Okay, so this will give us, we will keep the first row 1, 2, 0, and we have 2 here. For the second line, so we have -3 times row 1 plus row 2, so we have 0 here. Here we have 3 minus 2 is 1, -3 plus 1 is -2. Yeah, -6 plus 0 is going to be -6, and 0 minus 1 is going to be -1, and -6 minus 3 is -9. For the second row, I'm going to do 4 times row 1 plus row 3. Okay, so we have a 0 here, and 4 minus 4 plus 3 is -1. 4 plus 0 is 4, and 4 minus 8, sorry, 8 minus 1 is 7, and 0 plus 2 is 2, and 8 plus 5 is 13. Okay, so now the next step is to use in the second row, the leading entry in the second row, to cancel the entry in the third row. Okay, yeah, so let's go. We are going to do row 2 plus row 3. Okay, let me write it properly. Row 2 plus row 3. So minus 1, minus 1, 1, 2, 0. We have 0, 1, minus 2, minus 6, minus 1. Sorry, here is 2 and minus 9. And the last row is 0. And 1 plus 1 minus 1 is 0. Minus 2 plus 4 is 2. Minus 6 plus 7 is 1. Minus 1 plus 2 is 1. And minus 9 plus 13 is 4. Okay, so this is our echelon form of the matrix. So okay, we stop here for the echelon form. Maybe let me go to the next. Maybe we can have some space here, right? And continue the rest here. Yeah, that way we have everything on the same screen. Okay, so step 3, we need to do what? We need to describe the solution set. First of all, let's ask ourselves what is the type of solution we have. Okay, so we have arrived at the echelon form. Do we have a contradictory row or a contradictory equation? No, we have no contradictory equation here. Therefore, that means we have a solution. Either it's a unique solution or infinitely many solutions. Here we can see that it's infinitely many solutions because what? There are variables that are leading no rows. There are variables for which we don't have a row or rows where they are leading. So for the first row here, we have x is leading. So here are our variables. For the first row, x is leading. For the second row is y that is leading. And for the third row, we have z, which is that is leading. But we don't have rows where w and u are leading. Therefore, we have infinitely many solutions. Okay, so now let's do parameterize the solution set. Okay, so let's parameterize the solution set with the free variables. If you recall the definition of a free variable is a variable that is not leading. Okay, with the free variables. So this is the back substitution part. Okay, so this is back substitution part. So okay, let's start with the last row. So row 3. We have what? We have 2z. Okay, so coefficient of z is 2, coefficient of w is 1, and coefficient of u is 1. So we have 2z plus w plus u equals to 4. Okay, I hope you will make the difference between my u and my 4. I hope so. Okay, so this is u, that's 4. Okay, that's how we have to write down the u, the last row. Okay, sorry. So we need to write the leading variable in terms of the free variables. Therefore, here we have z That means we have z that is equal to, so we bring first of all, so let's say 2z equals to 4 minus w minus u, okay, and divide by 2. So we divide everything by 2. Everything here instead of 4, okay, we will have 2. So 4 divided by 2 is 2, and when it comes to w, it's going to be minus a half, and minus half there as well. So let me give myself plenty of space. So minus a half w minus a half u. Okay, so that's row 3 done. Now row 2, we have okay, y minus 2z minus 6w minus u equals to 2. Okay, so that's our row 2. That means y is going to be equal to 2, okay, minus no, plus 2z plus 6w plus u. Now we know the value or the expression for z, so let's sub it in. So we have 2 plus 2, z is 2 minus a half w minus a half u. So that's going to be 2 plus 4 minus w minus u. That means y is going to be equal to, we have here 6 minus w minus u. Okay, that's my u. That's the description of y, and I hope I wrote everything well. Okay, yeah, we are missing here, look, we are missing the 6 plus 6w here and plus the u. Uh-oh. So let's have a look. Okay, so we have the plus 6w here and plus u. Therefore our y is going to be equal to 6 plus 5w. So it's just 6 plus 5w. The u's are cancelled. Okay, now step number no, we are not finished yet. Sorry, we are not finished yet for row 3. So that's row 3. Row 2, now we have to deal with row 1. How do you write down row 1? Row 1 is written as, okay, let me go a little bit down to give myself plenty of space. You will not be able to finish everything on this screen, so we will go to the next one. Okay, okay, row 2, we have minus x minus y plus z plus 2w equals to 2. Okay, so we are working with the echelon form of the matrix, and so let's write, so x is going to be equal to minus 2 minus y plus z. We now know, okay, let me write it down anyway, plus z plus 2w, which is going to be equal to minus 2. Now we know y is 6 plus 5w, and we also know z is 2 minus a half w minus a half u, and we have plus 2w there. Excuse me. Okay, so let me go here. So we have x is going to be equal to minus 2 minus 6 minus 5w plus 2. So here, okay, let me minus half w, let's write it all, minus half u plus 2w. So let's group the constants together. So minus 2 minus 6 is going to be, okay. Let's make sure we have everything done correctly. Okay, here just check, let's just double check. Okay, plus 6 plus 4, okay, we have 6 plus 2. Okay, and when it comes to x here, okay, let me just double check to make sure we have everything written down correctly. So we have 2 there, okay, minus 2 minus y plus z plus 2w, so we have minus 2 minus y here plus z, z is that, plus 2w. Okay, yeah, I think everything should be okay. Here, yes, everything should be fine. Okay, let's go. So we have minus 8 here, okay, and for we have minus 5w plus 2w is minus 3w, and then we have minus half w, that's going to be 2, minus 6 minus 1 minus 7w is going to be minus 7 over 2w, and then for u we have only one term in u, minus a half u. Okay, so that's our x. Oui, I see. Okay, row 1 is 4 here. Row 2 is minus 9. Why did I write minus 2, 2 there? Sorry, 2 there. Uh-oh, I know. Okay, so that is minus 9. Minus 9. Okay, forgive me. So here is not 2. Everywhere we have 2. I have to change it with the minus 9. Okay, minus 9, minus 9, minus 9. So here is just going to be minus 5. Okay, plus w. Okay, okay, yeah. So yeah, okay, it changes a lot of things. It changes a lot of things. Okay, so it's going to change a lot of things here. Okay. Okay, so here our y is minus 5 plus 5w. Okay, and yeah, so now we have minus 2. How we got this one right? Yeah, we have minus 2 plus 5 minus 5w plus 2 minus a half w minus a half u plus 2w. So let's group the constants together. We have 5 here, 5. For the w's, we have minus 5w plus 2w is minus 3w, and so we have already done this one. So it's going to be minus 7 over 2w and minus a half u. Okay, so we have the x as well. Okay, so if you can see here, we have each variable, each leading variable parameterized with the free variables. Okay, so let me go to the next screen with the step 4. So step 4, uh, now we have to describe the solution set. Okay, describe the solution set using vectors. Okay, vectors notation. So if you recall, we have just described x, y, z. So here, if you recall, we had our z, which was equal to 2 minus a half w minus a half u. Okay, so we have here z is 2 minus a half w minus a half u, and y is minus 5 plus 5w. So here we have y, which is equal to minus 5 plus 5w, and x, which is equal to 5 minus 7 over 2w minus a half, sorry, minus 7 over 2w minus a half u. So we have 5 minus 7 over 2w minus a half u. Okay, so how do you describe the solution set? The solution set is x, y, z, u, sorry, w and u. Okay, so we have x, y, z, w, u. So that's the solution set, or the variables for our solution. But we have just parameterized them. Okay, so we said that x is equal to, so we write the x there, 5 minus 7 over 2w minus a half u. That's x. When it comes to y, we have minus 5 plus 5w. And for z, we have 2 minus a half w minus a half u. For w, we just have w, and for u, we just have u. So we have just learned vectors addition. So let's rewrite these entries. This vector, let's split this big vector into into 3 vectors. Okay, so the constants first. So here we okay, for the last two one, let me, for visualization purposes, let me rewrite. So y, w is here in this column, and the u is going to be here, u. Okay, so what we have here, we have on the, so we have on the first column we have the constant in this big matrix. In the first column we have the constant, in the second column we have the w terms, and in the third column we have the u term. So the u terms, so we can split this big matrix into three small matrices. So we have 5 for x, minus 5 there, and 2, and for the last two rows we have 0, 0. Okay, so that's that one, plus we have here the w terms, so we have minus 7, okay, over 2, 5 minus a half, and here the coefficient there is 1, and we have 0, multiplied by w. Okay, we have done vectors additions and scalar multiplication. That's why we have revised them to be able to write down the solution set of linear system in a more elegant and beautiful way. Okay, so plus minus a half, okay, 0, minus a half, 0, and 1. multiplied by u. So if you add these three vectors together, you will get this big matrix, okay? So this is going to be, let me write the final form of the solution. Let me write it in a different color. Oh, let me write it in green. The final solution is written as follows. So we have x, y, z, w, u, okay, equals to the first vector is 5, okay, is 5. In the next video I will explain the description of this solution set. Minus 5, 2, 0, 0, plus minus 7 over 2, 5, minus a half, 1, 0, w plus minus a half, 0, minus a half, 0, 1, and u. So such that w and u are free. That means they can take any value in R. So that's how we solve a linear system of equations. That's the solution set. Isn't that beautiful? And in the next video, I will explain these vectors have names. This one, the first vector, and then the last two vectors, they have particular meanings. Okay, so it's very beautiful when you write the solution set like this. Okay, so I think I'm going to stop here, and I will see you in the next video. With we will continue, okay, with part 5 of this chapter. Okay, so I think I'm going to stop here. Thank you, and see you.